Hello guys, welcome to this tutorials in which our main aim is to understand the implementational details of generative adversarial networks. In the theory sessions, by now you would have been comfortable with the mathematical nuances that are there in terms of generative adversarial network, which is a special case of variation divergence minimization. So, we have chosen a specific f function, and because of which now we get this particular thing, which is generative adversarial networks, which is a saddle point problem. We will be going ahead and looking at the implementational details of the generative adversarial network. So, without any further delay, so let us jump into the discussion. Now, we all know that this is the generator network. So, wherein which you will be sampling from a normal distribution, and then you will have a neural network. So, and then you will pass this through the neural network, and then you will be obtaining the samples from this p theta distribution, and then you have this discriminator, which is a binary classifier, now wherein which you give this x or x hat. Now it should be giving the decision. Now what is the decision? This is a probability that this is real given the given images from the real distribution. Okay, it is from px. Okay, this is what we look at it as an output, and then we want the system wherein which this discriminator actually fails. So that means that post training, so the values that comes out of the discriminator, either you give a real image or a generated image, so it should be giving 0.5, now which is an indication that we have obtained good samples wherein which the discriminator is not able to discriminate between the real images and the generated images. Okay. So now we all looked at this is the loss function which is there, and please see this, there are two terms here, these are the two terms that are involved. So wherein which the first term, the expectation is over the actual data. Now this is over the generated data. Now we can replace this x hat which is there using z. Now when z is sampled from normal 0i, that also is the way of looking at it. So now so there are two sets of parameters. Now there is theta and there is this w. So now we will be maximizing with respect to this w. Okay. So we can see this, both the terms now contains this w, this set of parameters w. So now we can approximate this expectation which is there using the sample averages and the batches. So this is the samples from the real data, and this has to be calculated over the samples from the generated data. Now how do you get this xj hat? Now we get this xj hat, first we sample from z, and then we will pass it through the generator, and then we get this xj hat. So now that means that to go ahead and update the weights of the discriminator, now we need the sum of these two terms, and then we need to maximize this. Okay. Now in contrary, if you want to obtain the theta, which is the parameters of the generator, now we can see this, now this is the same two terms, we can see that the first term which is there is independent of theta, so therefore we do not need to consider this. So we only need to go ahead with the second term. Okay. So and then we want to minimize this. Okay. Now see here, whenever I am saying that there is a generator, I am not bringing in any kind of architectural predispositions. So the way in which we implement in today's discussion is, now first we will be going ahead and using a very simple multi-layer perceptron as generator and discriminator, and then we will be implementing the vanilla GAN, and then using the same generator and then the discriminator setup, where in which we have used MLP as generators and discriminators, we will be going ahead and implementing the conditional GAN. So, I am assuming that all of you are pretty much aware of conditional GAN, where in which Y is added as an additional input. So, the label information is also provided. Okay. So, we will see the nuances as we go along, and then rather than using multilayer perceptron, we will be going ahead and using deep convolutional networks. So, we will be implementing DCGAN, which is just the architectural modification of vanilla GAN. Instead of using multilayer perceptron, we will be going ahead and using a deep convolutional network, and then we will be using transposed convolutions for the generator, and then we will be using the plain convolutions for discriminator. Okay. Now, we will see the all those nuances as we go along. Okay. So, now the first thing, so we need to install a couple of packages. Now, why do we need to install is, see, once the images are generated, how do you know the quality? Is there any numerical metric that is there using which we can estimate the quality of the generated images? Now, as it turns out, we have what is known as FID scores. Okay. So, this FID score, now what we do is we use the inception net. So, we would have looked at the inception net earlier in our PyTorch CNN discussions. So, we take an intermediate layer. Now, see, the idea is like this: you give an image and then you get an embedding out from the middle of a CNN network. Okay. So, now those intermediate representations are used to compute this FID scores. Okay. Now, that is what this computation is all about. So, for that we need special packages. So, we need this torch metrics which are there, and one more thing, see, GAN training is pretty time consuming. So, therefore, what I have done is I have already ran all these things. So, therefore, we will be looking at only the outcome of this. So, we will not be live coding, we will be just looking at the output. Now, this is the packages that are needed. Okay, we install this torch metric package which is there. So, and then the next set of libraries that are needed is we need this torch. Okay. So, torch NN optimizer, and then data loader, dataset transform. So, make grid is used to have a kind of a grid kind of a structure for plotting the images, and then you need matplotlib and numpy. These are the standard libraries that we have been using overall, so on and so forth. So, then the next set of code which is there is to take care of the device configuration. So, first we will be looking whether the GPU is available or not. If the GPU is available, we will be using the GPU. We have the whole code is implemented with GPU enabled system. So, we used the same Google Colab which is there. So, that is how we have used. So, see, running this without GPU is possible. You need to make the network much more shallower. But the problem is it will take too much of time. So, please be aware of it. So, and then we will be using the MNIST data. Okay. So, we will be using the MNIST data that we have. So, here we will be preparing the MNIST data set. See, the need for this specific preparation of MNIST data set is quite simple. See, the generator outputs. So, normally we will be having a tan H activation at the end of the generator output. See, and the tan H value will be between -1 and 1, but the original MNIST data which is there, the issue there is it will be intensities between 0 to 255. So, then what has happened is we have normalized, the data will be normalized, therefore, we will be getting the values between 0 and 1. See, the actual data which is present is values between 0 and 1, but preferably for better implementational nuances, we will be using tan H at the end of the generator in each cases. So, therefore, there will be a mismatch in the range of values. Now, therefore, what do? We need to convert this 0, 1, the range of the actual images which is between 0 and 1 into -1 and 1. That is what we are trying to do. We are trying to normalize this. See, the x which is there, so we will be subtracting 0.5 and then we will be dividing by 0.5. Now, therefore, the 0 which is there will be converted to -1 and then 1 which is there will be converted to +1. So, this is how we normalize. So, you can see it here. So, we have composed the transformation. We will be first converting it to a tensor, and then we will be normalizing with mean 0 and standard deviation 0.1. Since it is only one channel image, we are using MNIST, which is only one channel image. Therefore, we have only provided one number here. So, if you are going ahead and implementing this for any other data set which is having a 3 channel data, now it is good to use ImageNet statistics. So, that is publicly available. So, any 3D data, in the sense any 3 channel data that you are going ahead and using, now it is good to go ahead and use the ImageNet statistics that are available. Okay, fine. So, and then you are downloading the data sets. So, the batch size that we are considering is 128, the standard ideas. Okay. So, this we have seen again and again even during in our the PyTorch discussions that we have, and I am assuming that these are clear. So, and then what I am trying to do is I have taken some examples from a batch. So, okay, each batch, since my batch size is 128, I am getting one batch of things, and then I am only picking 32 of them. So, and then I will be going ahead and plotting it just to see that now these are the real images that are there. See, real images in the sense these are the images that are provided to us. Okay. So, the actual images we have taken out of 128, we have taken the first 32 of them, and then here we are showing. So, this is just for the sake of reference, so that once we generate the image, it has to be close enough to the way in which it is looking. Okay, good. So, now then we need the hyperparameters. So, for vanilla GAN, the hyperparameters that we will be using is the latent dimension that we will be using is 100. So, that means that the z which is there, we will be a vector in 100 dimension. It is a normal vector in 100 dimension, and then the image size that we are getting is 28 cross 28. The learning rate that we will be using is 0.0002. We will be using the same learning rate. See, since we all know that we need to optimize 2 sets of parameters in GAN, and one set of parameter we need to maximize, and in the another set of parameters we need to minimize. Now, therefore, we can have multiple learning rates, which is perfectly fine. Even in implementation we can go ahead and do it, but what we will be going ahead is we will be using one set of one learning rate for both generator and then the discriminator. This is the choice that we are making. Okay, we are going ahead with number of epochs as 25. Okay. So, now let us look at the generator architecture. So, we are using MLP here. So, now let us look at this architecture. Okay. So, now first nn dot sequential, we are having 100 to, so latent dimension is 100. So, we have 100 to 256, okay, and then we are using leaky ReLU as the activation function now which is there. So, which we have used earlier also during our discussions. So, we have using leaky ReLU here. So, and then we will be having 256 to 512, again leaky ReLU, and then 512 to 1024, and then 1024 to 28 cross 28, which is 784. Now, this is your generator, and then at the output we will be having the tan H. So, just to reiterate, so the network structure, so it will be the first is 100. So, from 100 we will be going into 256 and 256 to 512 and 512 to 1024, and then 1024 to 784, and this you will be going ahead with tan H operation. So, you will be having the 784, and finally whatever is the 784 we will be resizing the after this tan H we will be resizing it, and then you will be getting an image which is 28 cross 28. Okay. This is what will be the generator. Okay. So, now let us look at the discriminator part, okay, and the forward thing. So, you just pass it through the generator, and then the discriminator. So, the discriminator that we are having is you will be giving an image, and image will be having 784 features. Okay. So, 784 to 512 will be again using leaky ReLU with the leak of 0.2, and then 512 to 256 and 256 to 1. Why we are going ahead with a binary classification problem. Okay. So, that means that the architecture, this is the generator. This is the generator that we have, and then the discriminator discriminator, it is this is 784 okay, I myself forgot, to 512, 512 to 256, 256 to 1. So, and then and please remember here, I have also put it in comments here that after this please do not use sigmoidal activation, because we will be using the loss with logits. So, it will be converted, it will be taken into consideration. Okay. So, please do not have any kind of sigmoidal activation here. We will be having the BCE loss with logits. So, I will tell you how it works. So, and then you just pass the thing. So, this is just the forward through this n dot sequential that we have. Okay. So, now then we have to create the instances of this generator and discriminator. Okay, you just provide the input as the latent dimension. The latent dimension that we will be using is 100. Okay. So, and then you create an instance of generator, you create an instance of discriminator. So, and then you print the generator and then the discriminator, and you can see it here. So, 100 to 256, 256 to 512, 512 to 1024, 1024 to 784. So, and then lastly you will have a tan H in the generator, and then the discriminator will be 784 to 512, 512 to 256, 256 to 1. Okay. So, and then there is no activation function post this. Okay. So, now what is the loss that we will be using? The loss that we will be using is BCE with logits. Okay, this is the loss. I will define how does it mathematically mean, and then the real images that are there I will be indicating them with 1, and fake is indicated with 0. See, rather than using the word fake, which we will be using anyhow, so it is good to use the word generated. Okay. So, and then the optimizer for generator and discriminator, see, you can immediately see here. So, you are providing the learning rate. This is what I was indicating earlier. We can have different kinds of learning rates for generator and then for discriminator, and then since these are two different optimizers all together, we can have different optimizers as well. So, you can use ADAM in one case, SGD in another case, and then see how does it has impacts on the outcome, and what do you mean by an outcome, because these are images. Again, these sampled images has to be what do you call, measured using FID score, and then that is the metric that we will be using. So, now going back to this, what is this BCE with logits loss? Okay. So, now let us look at it. So, now so the real examples we mean it, so it is a binary classification problem, we mean 1, and then the generated examples, so we mean it by 0, and then what is this BCE loss with logits? So, this is BCE loss with logits. Now, let us say that the logits that is coming out, we will call this as as A is the logits, and then Y is the label, okay, that we have. So, then how it looks like is, so it is Y log sigma of A plus 1 minus Y log of 1 minus sigma of A. Okay. This is what we mean. So, see, Y can take value either 0 or 1. If Y is 1, now this term will be taken into consideration. If Y is 0, this term will be taken into consideration. And how does it help us in optimization? Now, when we go into the training aspects, I will delve it in much more detailed. Okay. So, now this is the BCE loss with logits. So, now let us look at the training aspect. Okay. So, we already have the, so the first thing that we will be doing is we will be putting this generator and discriminator in the training mode, and then we will be going ahead with the whole of the data 25 times, because we have decided the number of times that we will be looping through is 25. Running loss I have kept 0 and 0, these are bookmarkers, so let us not worry about them. So you take a batch of examples. Now then what do? First you go ahead and get how many examples are there. Now what is the batch size of the examples you get, this is again for bookkeeping. Now then whenever you are getting the images, so that images will be coming from CPU, it will be located in the CPU, therefore what do you need? You need to port it into the GPU, that is what you are doing here, real image.device, we already know this. So now then the image that we have will be a matrix which is 28 × 28 matrix. So but since we are using MLP, so what we will be going ahead is, now we need to convert it into a vector. Now why do we need it? We already have the image. Now the question is why do we need it? Now let us go back to the loss function that we have. Okay. See, it takes, as you can see here, it takes xi as an input. Okay, as you can see here, it takes xi as an input. So you take this xi, pass it through the discriminator which is there. Okay, this will be the output of the discriminator. Fine. Now this is for xi. Now xi is sampled from px, so which is the actual data distribution. So for which we have put as 1. Okay, and then you can see this here. This is for xj hat which is there, the jth example now which is there. Now this is the generated example. You take the generated example and pass it through the discriminator 1 minus of it. Okay, so when will this be taken into consideration? Now it will be taken into consideration when we have the generated image. So now into this, if I have, so if I put yi and yi hat. Now what is yi hat? It is not the actual labels of the images, either it is real or fake. If I put this, now this will be only there for real images, so it will be 1. So 1 minus yi, it will be 1 only when this yi will be 0. Okay, this resembles our BCE with logits. Therefore we are using this. Okay, now it is the choice that we made to go ahead. So now you are making it into a flattened vector. Okay, that is what we are going ahead. So now the first thing we are going ahead and training the discriminator. First, since it is going in the loop, there might be some gradients that are accumulated from the previous step. Now therefore what do? We clear off all these gradients which are there. So the discriminator gradients has been cleared. See, we are going ahead and training the discriminator. So that means that we are optimizing for what? We are optimizing for W. Okay. So now since we are optimizing for W, so now let us proceed. Now first you take the real images and then you pass it through the vanilla discriminator, so you get the output. So what did you get? You get dw of xi. Okay, so let's look into it. So you got this, you got this dw of xi. Okay, fine. So this is what we have got. So now we are making all these targets. So real targets torch.ones for the batch size. This is why we needed the batch size, wherein which every entry is 1. That is why we have taken torch.ones of a column and then you are porting it onto the device. So now you use this and then you go ahead and give real output and then real targets. So all your real targets are 1. So now if you go ahead, for each example this y which is there is 1, therefore you will only be getting this term. Okay, now please remember there is a negative sign here. Okay, so you will be only be getting this term. Okay, so when which what is this a? So this a is logits, this a is nothing but dw of something. Okay, now whether it is an actual image or a generated image, it does not matter. So you have this dw of this. Okay, so and then these are logits. So once you take the sigmoid, it will become the decision of that binary classifier. So this term I get for one example, this is exactly what I wanted for one example, okay, and I get it over all the real examples. I get this term, okay. This first term is what I have got, okay. Now please remember, there is a minus here, you take that minus, therefore this maximization problem will be converted into a minimization problem. And why is this important? See, because when you use this optimizer dot step, it only performs gradient descent, okay, but this W which is there, now we need to perform gradient ascent. Now therefore that is again one more reason why we have used this BCE loss. Now since you have that minus, so what you will be getting is minus of this, so you can take this, so this will become a minimization problem, and then you can use the optimizer dot step. See, these nuances needs to be taken into consideration, okay. Now these are very important, otherwise sign mismatch happens, so you will be optimizing totally a different objective and then you might be diverging from what you want, okay, fine. So I got this first term, and then this maximization, this negative sign I have already told, so let us not worry about it now, fine. So now I got this loss, so which the first term which I am calling it as real loss. Now I need to go ahead and generate the images. So now what I need? So I need the samples from the normal distribution. How do I take the samples from normal distribution? I know torch.randn. So the batch size, which I am keeping it as 128, and then network is agnostic of batch size, that is totally fine, which we know from our earlier discussions. So latent dimension is where which each example is a vector of 100. So and then you pass that through the generator, okay. So now we need again please look at this, you need this xj hat. How do you get this xj hat? You sampled z and then you pass this z through this discriminator, okay. To do that, first you have to get this xj hat. How do you get this xj hat? This xj hat is obtained by passing this z through the generator, okay. Now that is what we are doing now. First you are passing it through the generator and then you are getting the fake images. So now it has passed through the generator. Now please remember, it will be having the computational graph information. Now therefore it will be coupled with the parameters of the generator, but we are going to update the parameters of the discriminator, therefore we want to decouple it, okay. So now that is the reason why we use this fake images dot detach. So in which we are decoupling the flowing of gradients, so detach prevents the gradients flowing into G. So we only want to update the weights of the discriminator, okay. So now you take this, so you detach the thing and then you pass it to the discriminator, that will give you the fake output, okay. Now that is the logits that we have got, I am naming it as fake outputs. Now then what will be our targets in this case? The targets will be torch.zeros, now in which all the examples will be zeros. So now what has happened here is the y, so the y that I will be getting will be all 0, therefore what happened, this term will be off, okay. So 1 minus y will be 1, so therefore this will be there, so therefore it is log of 1 minus of dw of this, okay. These are the generated images in the case. So this is what the term that we wanted, this is the second term that we wanted, which we got. So log of 1 minus of this logits, so it is not logit, it is the sigmoidal output, we will be having sigma of a in this case, okay. Now that is what you can see it from here, okay. And then again it is sum of two negative terms, so this is again a negative term, this is again a negative term, each example, and that summation will be sum of all the negative terms. So you can take that negative sign outside, so then this will when you take the sum, now finally this will turn into a minimization problem. So it will not have any impact on the objective that we want to go ahead and maximize, okay, fine. So we got the targets and then you get the criteria. So what is the total loss? Real loss plus loss real plus loss fake. Now that is the loss with respect to the actual examples, the loss with respect to the generated example. So what do I mean by that? The first the summation and then the second summation is what do we mean. Okay. So now please understand that this is not, see, when we give mathematical treatments, we need to use these similar terms that are there. When you go out and see some of the other repositories, there you see these terms. So if you do not introduce these terms, it will be a different kind of a trouble. So now please remember these two terms that we have is summation that we have, the first term and then the second term is what is being summed. So what is that I am saying is, you are actually getting this is what I am saying. Okay. This is because of the samples from Px. Now this is because of the sample from P theta. Okay. So I want to equate this. So fine. So you have the total loss. Now then you what you do? You go ahead and perform loss dot backward. So and then optimizer dot d step. Okay. So you go ahead and get it. So this will update the parameters of the discriminator. Okay. You have updated the parameters of the discriminator. Okay. So now, so what did we do here? See, we updated only the weights of this particular discriminator that we have. We updated the weights of this discriminator. We use these two sums and then we did it. So now we need to update the weights of this generator. Now then what we want to do? Now these weights of, so again if you want to update, how do you update the generator? So you need to compute this particular term. Again, so generator parameters are there and then the generated things has to go through the discriminator. So then how do we do it? So we update only the theta with this w. So even though you pass this through the discriminator, so this w will be kept constant. Okay. So now let us see this in implementation. So now first optimizer dot zero grad. So we clear them off. So and then fake output. So how you get these fake images, so which are there, which we have already generated. You pass it through the discriminator and then here we have torch dot ones. Okay. Now here I just want you to give an alternative viewpoint that we will be going ahead and implementing. Okay. So now we already know that the theta star that we want is the theta star that we want is arg min of theta, which is 1 over b2. This is summation j is equal to 1 to b2 log of 1 minus dw of g theta of zj. This is for log. Okay. Fine. This is what we need to optimize. This is the equation that we should be optimizing. Okay. So theta, how do you update? Theta minus some learning rate. So the gradient of this with respect to theta and w. Okay. This is the update rule that we have. So now we will not be going ahead and implementing this equation. So even though we got this equation, we will be going ahead using another objective now, which is known as the non-saturating objective. Okay. The reason is implementational nuances. It has nothing to do with the theory aspect of VDM that we have looked into. So now let us look at it. The optimization that we will be going ahead and doing will be using this theta star, which is arg min of theta. See, I prefer to retain this arg min. So minus 1 over b2, this summation j is equal to 1 to b2 log of dw g theta of zj. Okay. So now see that you do not have any equation for log of a minus b. See, that is not what I am doing here. Okay. Now this is a totally a different objective altogether. Okay. Now this objective which is there is what is known as this objective has a name. Now this is non-saturating objective. Okay. Now please remember these are two different things, two different mathematical functions, but they provide the same end result. Now what is the end result that we want? That is what I will show you. Okay. So just making the point. Now these are two different mathematical functions. So two different mathematical functions, but provide same end result. How does it provide same end result? That is what we will discuss. So now see, now let us consider this as the outcome. No, not consider, it is the outcome of the discriminator. So now let us call it as P. So let us P is dw of g theta of z, and then once you apply the sigmoid, now this has to be between 0 and 1. Now what is this? This is the probability that this is from a real example given some x hat. Okay. Now I am explicitly writing x hat because we are only considering the generated samples here, and even in this case or in this case we are only worried about the generated samples. Okay. So now if you take one example, what does this boils down to? Now this is 1 log of 1 minus p, this is minus log p. Now this will be log of 1 minus p, now this will be minus log p will be the thing. Okay. So now let us call this as loss 1, which is what we have obtained. Now that will be log of 1 minus p, and then the non-saturating thing that we have, non-saturating optimization objective that we have, that is minus log of p. Okay. Now let us take a case now wherein which the outcome of the discriminator, the p value that we have got, p is 0.1. The p value that we have got is 0.1. Now let us see what happens in both of these cases. Now in this case, so in L1, now what is log of 1 minus p? Now this is log of 0.9. Now this is minus 0.105. In the other case, this is minus log p. Now in this case, now this will be minus log of 0.1. Now this is 2.303. Okay. Fine. So what? I got two different values. So what will be your question? Okay. Now valid question. So now what is that we want in both the things? This is also a minimization. We want to minimize this term. Okay. So if you see, this is summation. So you want to minimize this term. So individual terms you have to go ahead and minimize. Okay. So in both of these cases, so you want the minimum value of log of 1 minus p. Here also we want the minimum value of minus log of p. Okay. We want the minimum value that p take. Okay. Yes, we are optimizing the parameters, but the value that p is coming because of the interaction with the parameters. Fine. So now, so what do we mean? So we want 1 minus p to be smaller. Now then what do you want to do? Then you have to increase p. That is what we need, right? In this case, similarly, even if you go ahead in this case, it will turns out you need to increase p even in this case. See, even though the objective functions are different, now both of them, if you implement, if you go ahead and understand, both of them want to increase the p value. Okay. So now what does this mean? So both of these functions, so both of these say increase d of g of z. Okay, both of them want to increase this, fine. So now you want to increase, now how do you increase it? You can only modify the parameter. So we want a stronger push, okay. So we want it to go there faster. So whichever gives you the gradient which is stronger, I will use it. So now I want to go ahead and compute the gradient, okay. So now what is this P? This P is sigmoid of whatever activation A that we have, okay. So now how do we get this? So now what is L1 is log of 1 minus P. So you want to, what do we want? We want this, the gradient with respect to the activation, and then from there it will go into the parameter. So we just want to see what is this value. So now this, how do you calculate? Now this is so chain rule, okay. Now similarly in this case also, this is L2 is minus log of P. Now how do we obtain? So we want this is divided by gradient, this is, okay. Now now we want to compute. Now if this is the case, now what is this? This is P into 1 minus P, okay. So now this leave it. So you should be able to take the gradient with respect to sigmoid function. I hope all of you know this. This is what will be the thing. So when you take when you take the partial derivative of L1 with respect to P, so now what you will get? You will get minus 1 over 1 minus P, and this is P into 1 minus P, and this will be minus 1 over P into P into 1 minus P. Therefore what will be the gradients? So in this case the gradient will be minus P. Now in this case the gradient will be minus of 1 minus P, okay. Now this will be the gradient. So now let us take a couple of numerical examples and see what will be the gradient value, okay. So now I will give the P value. So this is for L1 it is minus P, for L2 it is minus of 1 minus P, okay. So now if it is 0.1, now okay, let us start from 0.01, simpler one. So minus 0.01, this will be minus 0.99. Now if this is 0.1, this is minus 0.1, this is minus 0.9. If it is 0.5, this will be 0.5, this will be 0.5. If it is 0.9, this will be minus 0. Okay, there is a minus here, sorry. This is minus 0.1, okay. Now we can immediately see from here, even though the direction in all the cases it is same, okay. The direction is same, but the second case is having a much more stronger magnitude, okay. Now therefore, now what it boils down to, now therefore I can go ahead and obtain this, okay. I can immediately go ahead and obtain this, fine. So this is the non-saturating objective which we have, is a better way of in the sense stronger way, better in the sense stronger way empirically in terms of obtaining the parameters. So that is what we just looked now, okay. Now fine, then what? Now there is another issue that happens. See, now this is for generated examples. Now we already know that the y, the label that we are having for generated examples is 0, but this term looks like this, this term, this is what it is if you use BCE loss, not this. This is what we thought for generated term. So therefore what do you do in this specific case? You just, even though you are working with generated examples, makes y as 1, simpler thing. Now therefore this minus of this, you will get minus of this, fine, and then that you are minimizing, problem solved. Okay, this is how we actually deal with it. Okay, now this and this are similar. Now the only difference is, now here, now y normally it will be 1 when it is real, but since we are, even though we are dealing with the generated cases, what do? You make y as the 1 so that the problem is solved. Okay, this is what we will be doing. So now you can see here targets, that is the reason why in this case the targets, the generated targets that you will have is torch dot once. This is the story behind this particular line. Okay, and then you use fake outputs and then the generated targets, and then you go ahead and update the parameters. The same old story continues. Okay, now this is how you obtain it, this is how you optimize for the parameters. Okay, so we have updated the parameters of discriminator as well as the parameters of the generator. Now I urge all of you, see here in each batch one time I am updating the parameters of the generator and one time I am updating the parameters of the discriminator. Now just try it out, try multiple times you train the generator and only one time you train the discriminator, and vice versa, multiple times you train the discriminator and only one time you train the generator. Just have a loop inside for each batch. Okay, so and then try it out and then see what kind of output will you get. Will it have any substantial increase or substantial alteration in terms of the values of the FID scores? Fine. So now yes, now you can see this is how the loss is modifying, that is fine. Now we want to generate the examples. Now whenever you how do you generate the examples? You just discard the discriminator that you have, you sample from Z, and then what do? You sample from Z and then pass it through the, you sample from Z and then pass it through the generator, you get the images. So first you need to get those random noise. So torch dot rand n, you are taking 32 examples. Okay, so 32, we want to generate 32 examples. So you are generating 32 noise vectors, each of them with 100 dimension, and then you are porting it onto the device and then you are passing this noise into the generator. Okay, and so you get 32 cross 784, that has to be converted into 32 1 28 28. Okay, now because we are dealing with vectors, therefore you want to go ahead and do it, and then what you do? So the values will be between -1 and 1, that again you need to convert it to 0 1. Now how do you do it? You just add to the generated images, these are numbers, so to that you add 1 and divide it by 2, so that will convert it into 0 and 1, and then you make a grid, you port the images got generated from the generator. Now you have already ported the generator through to the GPU, now therefore you need to use this dot CPU so that it can be ported back onto the CPU and then you plot it. Okay, and these are those 32 generated examples. Okay, see, I know these are quite bad examples, I am with you on that, but you can see at least 0 1 9, okay, 2 to certain extent is able to get generated properly. Okay, so this is regarding the vanilla implementation of the GAN. Okay, now what happens is, now let us proceed towards the conditional implementation. See, in conditional implementation what happens is everything remains the same, the only thing that changes is whenever you are going ahead and training, in each of the time you will be passing your either the real images through the discriminator, or you will be going ahead and passing the noise through the generator, you will be giving the label information with it. Okay, that is the difference which is there. Okay, now let us look at it. So let us look at the conditional. Now as you can see here, the only difference is, so rather than having one input you will be having 2 inputs. So, one will be the noise, the other will be the label information. Here also you will be doing the same thing. See, now the question is, how do you give y as an input? Now that will be our next question that needs to be answered in conditional GAN. And still here also we will be using MLP kind of architecture for discriminator as well as for the generator. How do you give this y? See, this z, now even though you keep it, this is a 100 dimensional vector, these are 100 numbers. If you give just 1, now it is a, so the label information is just one number in your whole input. Now here also this is x is a 784 length vector, and if you keep y as just a single number, it might not have the impact that we want. Now therefore, rather than giving y itself, we want to give some kind of representation of y. So there are multiple kinds of representations that we can think of. One straightforward representation is you convert each of this label into their respective one hot representation and then go ahead and do it. Now that is one way of looking at things. Now rather than that, there is another interesting way which is known as learned embeddings. Okay. Now what do we do is we learn the embedding of the number which is there. Okay. Whenever I mean learning, so it is not, these are, whenever we say anything is learnable, that means that we are saying that there will be some learnable parameters involved. So now therefore you will have some learnable parameters. Now then again you need to update this parameter. Now how do you do it will be the question, that I will show you in the program, but this is what you are supposed to do now. Okay, fine. Now so now let us proceed. So everything else, all the loss functions and other things remains the same. Okay. So now conditional generator. So the number of classes is 10, embedding dimension I am taking it as 10. You can modify this. Embedding dimension is what will be the length of the embedding vector that you are going ahead, what will be the length of y. Rather than 1 I am giving it as 10 numbers. So you can what do you call, you can have an increase over there, you can have a much more lengthier vector which can be given as an input. Fine. The latent dimension I am keeping it as 100, so what we had earlier. So now this is what is known as the label embedding. So nn dot embedding, so number of classes is 10, now the embedding dimension is 10. Okay. So number of, so what it will does it will come up with the matrix. Okay. The matrix will have 10 rows, and then since the embedding dimension is 10, it will be a 10 cross 10 matrix. Okay. So this is embedding for 0, embedding for 1, embedding for 2, so until embedding for 9. So you will come up with a matrix like this. This will be a 10 cross 10 matrix, where which each row represent the embedding of that specific label that you are going ahead. And how do we learn this will be your question. These are the parameters, and these parameters you are putting it in the generator. So how will the generator will look like? So now you have the parameters, so now it will be, so embeddings and then the generator, and whenever you want to update the parameters of the generator, you should get your gradients from the discriminator. So now anyhow you are going ahead and considering these weights of the discriminator which are there, you are not updating them, you are just passing the gradients in the reverse direction. Now do not stop at the parameters of the generator, just push it ahead to these embedding weights, where in which each of them are updated. Okay, this is how we do it. See, generator will get, so this generator which is there, now we will have so this generator, now we will get x directly. Now in the sense, what do I mean by x? You will get z from here, and then you will have another input that you will be getting, now which is you will have embed, you will get the label here. Okay. So now you pass the label and then you have this Z. Okay, these are the input. This label which is there will be passed through this embedding. So what do I mean by that? If it is 2, I take this second row which is there, and that and this will be concatenated and given as an input for the generator. Now this is what I mean by these embedding vectors are learnable. Okay. So fine. So for that you need this embedding. So nn dot embeddings. So this is for all practical purpose it is similar to nn dot parameters. Okay. So then now what happens is your input dimension will be the noise dimension plus the label embedding. So the label embedding will be a 10 dimensional vector is what we have decided. Now therefore it will be 110. And then you have the model which is exactly similar. So there to our previous architecture, no difference, but in the forward pass there will be a difference. Why? Now first you get the labels and you pass those labels through the embeddings and then you get the label vectors. Okay. Now this will be the first step. So you get the labels, you pass it through this nn dot embeddings, you get the label vectors. Okay. So and then you get this Z which is already given as an input, you need to concatenate and then proceed. So you have this random noise that you have, and then we have the information for the digit that is there. You concatenate them, torch.cat, concatenate them using dimension 1. So and then you pass it through the model. Okay. So in this case which is the generator. Okay. Now the conditional discriminator, how does it look like? So discriminator again that also needs to have a input that needs to be taken into the embedding. Now here also what do you do? Now here also you do the same thing. Let the discriminator learn its own embedding for the labels. Now that is why you have the label embeddings here, and there is no need that the embeddings that is learned from the discriminator has to match with the no. Now these are the parameters, it will be updated on itself. Now you will be only passing the label, okay, which is 0 to 9, any integer between 0 to 9, that will be converted into its respective embedding and then it is taken into consideration. Okay, fine. Now first you have the input dimension which is 28 cross 28 plus the embedding dimension which is that we are considering it as 10. Okay. So then so it is 794, and then you have a classifier now which input is 794 and then it goes on. So how will be the forward function? Exactly similar, you take the labels, pass it through the embedding, and then you go ahead and concatenate the label vectors that you have got specific to the discriminator, and then you go ahead and pass through the model. Okay. Now this is how the network structure of conditional generator and conditional discriminator will be. Fine. So then you initialize them, port it onto the device, you use the same BC loss. Now the updation will be the same now. Okay. There will be no change in the updation story. Now there will be a small nuance that is there whenever you are going ahead and training. Okay. So you get these optimizer set, all those the same stories now hold even now. Okay. So now here you get this batch size, you get the images as well as you need the labels. See earlier in unconditional GAN you do not need the labels. So now you have these labels. Now then what do you do? Now you take this real images, you flatten them up. Okay. So that is what you do, and then how do you proceed with the updation of the parameters of the discriminator? So first you optimizer.0grad. Now you have these real images and their respective labels. Here what do I mean by labels? It is 0, 1, 2, whatever is the label of that particular batch. You get the targets. Okay. So you get the targets, and then so the real outputs and the real targets you just pass it on through the criteria. So which is there, you get the first term in the summation. Okay. So which is with respect to this is log of dw of g of x, where x is from px is what you have got. Now you take the noise images, you take the noise. Okay. Now for that you have to generate the labels now. Now because you need to pass it through the generator now. So for that you need to specify the label. So torch.randint, you are starting from 0 and then the number of classes it is 10. So it will be generating random integers from 0 to 9 for whatever is the batch size. So now you have got the random label vector, okay. So where in which each element will be an integer between 0 to 9 is what you have got here. Now you take these labels that are there and then you pass the noise as well as the labels through the generator. Now that will give you the images. Now you need to go ahead and pass this again through the discriminator. Before passing it through the discriminator, you need to detach the these generated images from the generator. That is what you will do, and then you obtain the fake targets using torch.zeros. So and then you compute the loss, okay. Now this is the second term in the updation of W. Now then you add them, so you get the total and then you back propagate and then obtain the gradients and update the step. Now this is with respect to the generator. Now with respect to this is with respect to the discriminator, sorry, this is with respect to the discriminator. Now let us come to the generator part, okay. So now to the generator part, now first you need to clear off the gradient, okay. Now again you get the fake outputs. Now you already have fake images and then you have already generated the labels for them. See, whenever I am using the word fake, so what do I mean by that? These are generated, okay. So that is taken into consideration and then you obtain the labels here with using 1. Why 1? I have already explained in detail, because we will be not be using the function, we will be not be optimizing the function that we have, we will be optimizing a surrogate of it which has a similar and better implications on the weights, okay. So and then you get the loss and then you go ahead and update. The same old story holds on. So now to generate, you can generate a specific digit now, okay. That digit you have to give. Therefore what I am doing is here requested labels. So I am taking a list range 10, that means I will get 0 to 9, I am repeating it thrice. Now that is what I will be giving as an input. So the remaining things remain same here. Now you can see these are the images that are generated 0, 1, 2, 3 to 9, okay. See, so 0 to 9 I am able to generate. This is far better generation compared to what we had in an unconditional generation, okay. This is how we work with the conditional GAN, which is implemented using the MLP. Now DC as the DC GAN is just the implementation of the same thing using the deep convolutional networks. That is the difference that we have. Now let us look at it. Now we just need to, so see the unconditional architecture and then the conditional architecture, everything remains the same. The way in which we give the labels, the way in which we use the embedding, everything remains the same. So we just need to look at two different architecture. One is the deep convolutional architecture for generator and then the deep convolutional architecture for discriminator. In the discriminator we will be using the standard convolutional, and in the generator, now since we want to increase the spatial dimension, now we will be going ahead and using the transposed convolution. And how do we implement it? We just need to look at the network structure, okay. So now the DC generator, the deep convolution generator. Now first you have some latent dimension, let us say that this is 100, you are using nn dot linear. So using that nn dot linear you are converting into 12877, okay. Now that means you are getting a vector which is a number which is 128 into 7 into 7. Now then, now what will be your convolutional blocks? So transposed convolutional blocks. Now it will be first, it will have 128 channels to 64 channels. The kernel size is 4 and the stride is 2 and padding is 1, okay. We have already seen how does transposed convolution works in our earlier discussion. So you can refer back to that, okay. So now then, so it will have 12877. So that means that the vector which is there will be converted into a hyper volume which is having 128 channels, and then each channel will be of a matrix of say 7 cross 7. So the output will be again a hypercube which is having 64 channels. So and the spatial thing is 14 cross 14, fine. So and then you use batch norm 2D. So we have already seen what is batch norm, and then you will be using ReLU here. no specific, you can use leaky relu also perfectly fine. So then the next layer will be 64 14 14, that you will be converting into 1 28 28. So in channels is 64, out channel is 1, so kernel size is 4, stride is 2, padding is 1. So since it is generator, you will be having a tan h at the output, which is similar to what we have earlier. Now how will be the forward process? First you get the z, and then you get this x, which is b cross 128 into 7 into 7. Now that you need to resize into b 12877. So that is what you do, x dot view. So you will be considering the last 3 dimensions 12877. So the batch size dimension will not be taken into consideration. Okay. So that you pass it through the convolutional blocks, you get the image. Okay. Now this is regarding the generator. Now coming to the discriminator, the input is an image which is of size 28 cross 28, which is having one channel. So you will be using the standard convolutional 2D, one channel to 64 channel, kernel is 4, stride is 2, padding is 1. So we know how it works. Now here I am using leaky relu with 0.2 and in place is equal to true. Again from now you have 64 14 14, that you convert into 128 77. Okay, just for the sake of symmetry I am using this. Again you have the batch normalization. Now then you have finally you need to put this into a single number, right, that is the point of the discriminator. So 12877 to 1, you will have a linear layer for this. Okay. And how will be the forward? It is exactly similar. First you get the images. Okay. So then you obtain and pass it through the convolutional blocks. The convolutional blocks will give you a hyper volume which is having 128 channels, and the spatial dimension of each of them is 7 cross 7. That you flatten it out, that is what you are doing it here in line number 72 here, and then you pass it through the fully connected layer, that will give you a logit. Okay. So then you go ahead and initialize the thing. So training, everything is exactly similar, that we have no difference. Okay. So then I am taking some, I am sampling some things. Now this is the images that are generated using DCGAN. Okay. So using exactly the similar process, the only thing that is modified here is the g theta and dw which is there, rather than it being an MLP, now it is a convolutional blocks here. So now we will just do the repeat the same thing for the conditional thing. Now again you will have a learnable parameters. So then the latent dimension now which is the noise, so will be added to this embedding. So your input, so it was 100, now it is 110. So again in n dot linear you will have a similar operation. You just go ahead and use the similar structure, and finally you will have a tan h thing. So how do you get the labels, whatever labels you have got, you convert them into the label vectors, and then you concatenate them with respect to the noise that you have and pass it through the fully connected layer. So that first you get a vector which is 128 into 7 into 7. So that you are converted into a hyper volume which is 12877, and that is passed through the convolutional blocks. Okay. So to diagrammatically represent, maybe that would be a better thing. Okay. Now first what do? You have a fully connected layer. Okay. That will give you let us say that this is in this structure it is giving you 100. Now this will be giving a vector which is 128 into 7 into 7, that you are converting it into an hyper volume, now in which you will have 128 channels, and this will be 7 and this will be 7 now which is there. Now this you are passing it through the con blocks, that will give you an image which is of size 28 cross 28. This will be this structure. See, if you are going ahead with this is the generator structure. If you are conditional, you just add 10 here, now which will be attached to the embedding in the earlier notion. Okay, now then how will be the discriminator? So the discriminator, you have this 28 cross 28, that you pass it through the con blocks, that will give you an output which is having 128 channels, 7 here and 7 here, that you flatten it out and then convert into a vector, that is giving to a fully connected layer. Now this will be a single number. This will be the discriminator. This is the structure that we are using. Okay. So now let us look at this. Now how will be the conditional discriminator be there? Now you will be having this embeddings. Okay. So then what do you have? You will have this con 2D. Okay. So first you get all the convolutional operations and then you will have a fully connected layer which is there. Now let us see the how is it being done here. Okay. Now first you get the label embeddings. See the label maps which is there is converted into 28 cross 28. Why it is converted into 28 cross 28 not 10 here is for each image you are just adding it. Okay. So okay, maybe I should have explained it at this point. Okay. See here the label embeddings earlier we used to have it for 10. Now here I am taking it as 28 cross 28. Why? Now because each image is a 28 cross 28. So what I will be doing is now this label information which is there that I will be adding to it. Okay. Now that is what I am doing here. So you get this information and then you concatenate them and pass it through the convolutional blocks. Okay. This is what you will do. So okay, what do I mean by adding is I will be concatenating, maybe I should have chosen my words properly. So you have B1 28 28 and then labels will be again B1 28 28. So your input for the conditional discriminator will be a 2 channel image. Okay. That is used and then that you get the 128 into 7 into 7 vector and then that you pass it through the fully connected layer to get the things. Okay. So then the whole training process everything now will be remaining the same as we saw in the conditional vanilla conditional GAN. Okay. So I just want to show you the generated image. Now these are the generated images that we have. Okay. So now I am able to generate images. So from all the 4 different things. Now one is vanilla GAN, its conditional variant using MLP. Now vanilla GAN and its conditional variant using the convolutional blocks, deep convolutional blocks. Okay. Now I have obtained this. Now you can see this these images, the conditional DCGAN images that we have are far superior in terms of its thing. I am not saying that it is perfect. Now you can see that the 9 here they are there, but anyhow it is far superior than all the images that we have generated. Now we are running it only for 25 epochs. Okay, very small epoch. So it is far better in that case. Fine. So now how do you obtain the FID scores? Okay. So for that you need to import this fetcher in inception distance from this torch metrics.images.fid. So how do you want to just do it? It's quite simple. Now first the images that we have generated will be from -1 to 1, that needs to be converted to 0 1. So and then now here how do we do it? We just clamp it. So we should clamp it to 0 to 1. So that means that every value which is between less than 0 till -1 is just clamped. Okay. So now it is just a 1 channel image. So now what do? You just repeat it for the 3 channels. Now because the input for the inception net will be a 3 channel data. So therefore you just, so now you have the repeated image which is there, now which is used to compute the FID score. Now what do? You just say that how many features I want to extract. See this inception network which is there has multiple layers. Now which feature you have to take is what is being represented here. I am taking this 2048 features. So to this you are giving the image. Okay. So then I am generating 5000 images and then I am passing it through and then getting the number. Okay. That is all is this whole code about. So you can look at it. Now you can see here. So the number of images that I got is 5120. The score that I am getting is 21.5. See lower the better. Okay. So lower score is the better value. So similarly we did the same for all the different GANs, the 4 different ones that we have computed. I have just repeated the same thing. So it is a thing So you can see here, now these are the thing. For vanilla GAN we got 92.93, for conditional GAN we got 104. See, this is interesting. See, even though we thought in the conditional GANs images were generated good, but in terms of FID score, so vanilla GAN is doing better, but it's the same thing is reversed in terms of DCGAN. Okay, I am just plotting them, so you can see this here. So these are the plots. It just for the sake of plotting. So here now what I have done is I have just tried a nice experiment here. Now what is that I am trying to do is I am generating one noise. I am getting one noise vector that is of 100 dimension. Okay, I am getting one of it, and then I am trying to generate with different labels. I am giving all the 9 labels to it. Okay, the same noise with label 0, label 1, label 2, so on and so forth, and then I am generating this. So you can see here this, it's the same noise. So I am using conditional DCGAN here, the same noise, but the labels are different. Okay, you can see the output here, the same noise but the labels are different, and then I reversed it. Okay, same label with different noise. Okay, now that gives a output like this. Okay, so what does this mean? Your output is dependent on both the labels as well as the noise. Okay, more predominantly on the labels in terms of conditional GAN. Now it is pretty much evident from the example that we have same noise we have used, and then we provided different labels, we are able to obtain different images. Okay. Now this is what we have done. Now this concludes today's tutorials. So we just implemented in today's discussion, and then we saw the mathematical equivalence between the loss functions that we have obtained. So you are going ahead with some derivation, and then how is it translated into the loss function, we saw it. So that is what we will be doing throughout this course. Now whatever has been discussed in terms of mathematical thing, we will be seeing its translation, and then we will be seeing its one-to-one correspondence. Now how is the mathematical idea that we have is correspondingly modified into its coding what do you call things. Okay, so that is what we have discussed in today's discussion. We have used a single channel image. If you have compute at your disposal, now please go ahead and train it for nice other images which are 3 channel, and then you can make a nice block out of them. So this whole notebook, the link for this notebook will be made available in the description of this video, so that you do not need to code it or generate it again. You can use this existing code, and then you can go ahead and enhance it, and let us know in the comments how does the images that you have generated looks like. We will meet again in the next tutorials. Till then, have a nice day. Bye bye.